All right, let's dive into the wild world of high-tech 3D X-ray scans. Behind every one of those jaw-droppingly detailed images you see, there's actually a hidden battle going on, a fight against some really messy physics to get that perfect result. I mean, have you ever seen that? You've got this super advanced, crazy, expensive machine, but the image it spits out looks, well, like that. It's a blurry, streaky mess. So, what in the world is going on? Why does this happen, and what does it mean for the actual science we're trying to do? You see, these visual glitches have names. They're called artifacts, things like cupping or streaking. But here's the thing. They are not just ugly little imperfections. No, they represent fundamentally corrupted data. Just imagine trying to find a microscopic crack in a critical aerospace part when it's totally hidden by a giant dark streak. That kind of corruption makes the whole scan completely unreliable.
So where do these things even come from? Well, the problem, it turns out, lies right at the very heart of how most lab-based X-ray scanners work. It's something called the polychromatic problem, and it is, without a doubt, the single biggest culprit behind getting a bad scan.
Okay, so the main villain in our story today has a name: beam hardening. To put it simply, the X-ray beam that starts the scan, it's not the same one that finishes it. As that beam travels through the object, it actually changes. Its average energy gets higher, and that change is what ends up distorting and corrupting the final image. Let's just walk through exactly how this happens, step by step. First, the X-ray tube fires what's called a polychromatic beam. That just means it's packed with a whole spectrum of different energies. Now, as this beam hits your sample, the lower energy, kind of softer photons get absorbed first. They just don't have the oomph to get through. This means the average energy of the beam that does get through starts to increase. It hardens. And this is the critical part, because it completely breaks the fundamental math that this scanner relies on, this relationship between a material's thickness and how much it absorbs X-rays. And once that math breaks down, that's when you get all those nasty visual artifacts. So how do we fight back against this? Well, the first line of defense is actually surprisingly straightforward. It's a pretty basic but incredibly effective toolkit that's designed to tame that unruly beam before it ever gets a chance to cause a problem. And the strategy here is just genius in its simplicity. The thinking is, hey, if the beam is going to harden inside the sample anyway, why don't we just control that process ourselves before it even enters the sample? The whole idea is to use a physical filter to strip out those problematic low-energy photons right from the start. What you're left with is a much more stable, pre-hardened beam for the actual scan. In this toolkit, it's literally just a few simple plates of metal. You've got aluminum, which is kind of the workhorse for your standard everyday jobs. Then there's copper. It's denser, so it gives you much more aggressive filtering. And for the really tough cases, you bring out the big guns, tin, which is extremely dense and super effective at creating a highly hardened beam. Let's actually see this in action. So here is the energy spectrum of a typical unfiltered X-ray beam. You can see it's a really wide curve, right? Lots of different energies all mixed together. In this case, the average energy is hanging out around 62 kiloelectron volts, or keV. Now watch what happens when we pop in a standard aluminum filter. See that? The whole curve shifts to the right. It's literally chopped off those lowest energy photons, and the average energy has bumped up to 67 keV. It's a good start. Okay, next up, we swap in the copper filter, and whoa, look at that jump. The shift is way more dramatic. Copper has just aggressively carved out a huge chunk of those low and mid-range energies, and it's pushed the average all the way up to 95 keV. Big difference. And finally, here's our most aggressive filter, 10. It shoves the spectrum even further to the right, and what you get is an extremely hardened beam with an average energy of 114 keV. You can literally see how we've sculpted the beam, turning it into a much narrower, much more powerful tool. And when you look at all these results side by side, the impact is just crystal clear. We go from an unfiltered average of 62 keV to 67 with aluminum, and then all the way up to 114 keV with tin. It really shows you just how much control a scientist has over the X-ray beam, just by choosing the right little piece of metal. But what happens when a simple plate of metal just isn't enough? For some really complex materials, scientists have had to develop even more sophisticated, really brilliantly engineered solutions to sculpt that X-ray spectrum with incredible precision.
A fantastic example of this is something called the Thoraeus filter. It's this clever 3-layer sandwich of metals. First, you've got tin doing the heavy lifting, but it has this nasty side effect of creating unwanted fluorescent X-rays. So the next layer, copper, is put there for one reason, to absorb that fluorescence from the tin. But guess what? The copper then creates its own fluorescence, which is then cleaned up by the final layer of aluminum. It's like this cascading trap that leaves you with a remarkably clean, hardened beam. So cool.
Another really clever solution is the bowtie filter, and it's designed specifically for scanning cylindrical objects. Think about it. With a cylinder, the X-ray beam has to travel through a lot less material at the edges than it does in the middle. So this filter is shaped, you guessed it, like a bowtie. It's thicker at the edges, which dampens the beam more on the sides, making sure the exposure that hits the detector is perfectly even all the way across. Now, all of this filtering gets us way closer to a better beam, but it's still a compromise. The ultimate goal, the true holy grail of CT scanning, is to get rid of that whole spectrum of energies altogether.
What we really want is a monochromatic beam. That means a beam made of photons that are all at a single, perfect energy. This is the absolute ideal because it completely eliminates beam hardening artifacts. It's not a small improvement. It fundamentally transforms the scan from a qualitative picture into a precise quantitative measurement.
Now, getting there isn't easy, but there are a few ways. You can use crystal monochrometers, which basically use a crystal's atomic structure, like a prism, to pick out just a single energy slice from the beam. There are also new advanced X-ray sources that can create a beam that's almost monochromatic right from the start. And finally, there's some seriously powerful software that can go back and mathematically correct for beam hardening effects after the scan is already done.
So, okay, after all this talk about physics and engineering and filters and energy spectrums, why does any of this really matter? What's the big takeaway here?
Here it is. All of this effort, it transforms the CT scanner. It stops being just a fancy 3D camera that takes really cool pictures. It becomes a true metrological instrument, a precise scientific tool that can take trusted, accurate measurements of things like density, composition, and internal structure. And honestly, this quote from the source material by Francesco Iacoviello just says it all perfectly. The whole point is ensuring the XCT data we produce is not just a picture, but a measurement you can trust. That word trust, that's what this entire scientific process is really all about. So I'll just leave you with this thought. As we move into this new era of Industry 4.0 and digital twins, the ability to create a perfect digital copy of a real-world object is absolutely essential. And that ability, it all comes right back to taming the beam. So the question is, what could we build? What problems could we solve when we know for sure that we can trust every single pixel of data?